Okay, we're going to talk more about logarithmic equations, and in some of these situations we're going to have to actually graph the log, and we'll talk more about this a little bit later, but let's just kind of graph one of our logarithmic functions and see what it looks like. And we have y equals log to the base 2 of x. So this is what I want to graph. I want to graph this function, log to the base 2 of x. And it's really kind of hard to come up with the values because we have to think in terms of exponents. So for me, it's easier just to rewrite this as an exponential equation. Remember, my base is 2, my exponent is y, and my answer is x. So 2 to the y equals x, or x equals 2 to the y. Now, to me, it's a little bit easier because I can find values of y and put these in, and then I can get the corresponding values of x. So I kind of work backwards. So when y is 0, what would x be? So when y is 0, what's 2 to the 0? 1. And when y is 1, 2 to the 1 is 2, so x is 2. See, I'm just going backwards. And y is negative 1, what's x? Well, 2 to the negative 1 we know is 1/2. When y is 2, 2 squared is 4, so x is 4. And then y is negative 2, that's going to be 1 over 2 squared, or 1/4. So for me, it's a little bit easier to do it this way than try to find numbers that work for the x that give me a nice even y. So let's plot these points. So when x is 1, y is 0. When x is 2, y is 1. And when x is 1/2, y is negative 1. You see negative 1 there. When x is 4, y is 2. And when x is 1/4, just like this, y is negative 2. So I can get some nice values like that. Now I'll connect those with a smooth curve. I'm going to use a pencil so in case I mess up, I can erase it. And now you can see that we have an asymptote like we had with exponential functions, except instead of the asymptote being a horizontal line, it's a vertical line. In this case, it's the x-axis. It's going to get closer and closer to this x-axis, but never touch it. So in this case, the domain would be 0 to infinity, and the range would be negative infinity to infinity. All right, so you can see that. It's going all the way down, all the way up. It goes a little slower up, but it does go up to infinity. So that's what our function is. Now, what we really want to notice is that this is a one-to-one function. It's a function because it passes the vertical line test, of course, but it's a one-to-one function because it also passes the horizontal line test. In other words, if you take a horizontal line, it only crosses it in one place. So we can say that logarithmic functions are one-to-one. If that's the case, then if the range values are equal, the domain values must be the same because we can't have two range values, otherwise it wouldn't be one-to-one. So if the log to the base b of m equals log to the base b of n, if that's the case, then we know that m must equal n. In other words, if the range values are the same, then the domain values must be the same. Well, that makes it really handy when we're trying to solve these logarithmic equations that have logs to the same base on both sides. So let's take a look at this first example. And this is log to the base 2 of x plus 3 equals log to the base 2 of 5x minus 9. Well, if my bases are the same, and the range values are the same, then the domain values must be the same, so I can just rewrite this as a simpler equation. X plus 3 equals 5x minus 9. Well, that's pretty nice, isn't it? Because then we get to solve that simple equation. What I can do is I could subtract x from both sides, and I would have 3 equals 4x minus 9. I can add 9 to both sides, so I get 4x equals 12. Then I can divide both sides by 4, and x equals 3. Now you always want to check your answer because remember when we talked about our definition of logarithms, way back over here, and this is the definition I gave you of the logarithm videos, it says that x has always got to be greater than 0, all right? And you can look over here when you look at logarithms, the domain values are greater than 0. All right? So these have always got to be positive. So if I put 3 in here, I just have to check it. And 3 plus 3 is 6, that's positive. And 5 plus 3 is 15 minus 9 is 6, so that's positive. So we're okay. All right? But if we happen to get negatives, then we don't have a solution. It won't work. All right, let's try another example. Let's see if I can fit this in here. And this is log to the base 3 of x squared minus 2x plus 1 equals log to the base 3 of 26 minus 2x. All right? Now again, the bases are the same. So my range values are the same, meaning the domain values must be the same. So I can say that x squared minus 2x plus 1 must equal 26 minus 2x. Now I notice that the 2x's are, well, I've got a negative 2x on both sides. So what I can do is I can just add 2x to both sides. And I end up with x squared x squared plus 1 equals 26. Then if I subtract 1 from both sides, I'll end up with, I'm writing a little smaller here, but I end up with x squared equals 25. Well, if x squared equals 25, I'll kind of do this over here, that will imply that x equals the square root of 25, and that means that x equals plus or minus 5. So I got two possible answers. Now I want to check both those to make sure that that keeps this positive. So if I put positive 5 in here, I get 25 minus 10 is 15 plus 1 is 16, that's okay. And then 26 minus 10 is 16, that's all right. If I put negative 5 in here, that's going to be definitely positive because that's going to be positive, that's going to be positive 10. So that'd be 25 and 10 is 35 plus 1 is 16. If I put negative 5 in here, this would be 26 plus 10. So again, 36 on both sides would be 36. So that's fine, that both sides would be positive, so I'm okay. So I always want to check those to make sure that whatever value we put in here will make these positive. And in both cases it was 36. Okay? So if that makes sense, so those are a couple good examples that should help you there.